Okay, it's a great pleasure to introduce Nir Sharon from Tel Aviv University. Nir received his PhD from Tel Aviv in 2015 in the mathematics department, where he worked with Yoel Shkolnitzky and Nir Din. He was then a postdoc at Princeton University from 2015 to 2018 in the Meet Singers research group. And in 2018, he joined the faculty at Tel Aviv. We're very happy to have him with us today. And Nir, floor is yours.
All right, thank you. Is camera on? Okay, so, thank you very much, Will. Thank you for having me. Yeah, today I'm going to talk about approximation, the multiscale of manifold-valued curves. Mostly, I will talk a little bit about variant of the problem, and but let's start. So we start with some intro to this topic. So here I'm standing at the shoulders of giants. This famous quote describes well the challenge when you have while trying teaching it. But basically, we all know manifolds. So there are like topological spaces, locally looks like linear spaces. And although their global structure could be very, very complicated, locally they enjoy many nice properties. So other than these geometric examples, or you can imagine surfaces, there are also some notable examples that we will meet again and again during this talk, or in the form of matrix Lie groups. So here I just mentioned a few of them: the cone of symmetric positive definite matrices, of order n, orthogonal matrices, Euclidean group, and so on. So, but we are interested. The main objects are our manifold-valued curves. So, for start, we can imagine something like a trajectory on the sphere. It's really straightforward, and we're starting from a certain point and progress with some velocity. But we can also go to settings which are less geometric and try to visualize them. So here is basically samples of curves, but we can easily imagine how these curves look like. Although this is a very abstract curve, we're talking about a time sequence of matrices represent special Euclidean elements, that is rigid motion that preserve orientation. And here we look at how the sequence basically acts on some object. In this case, these three axes drawn in red, blue, and green, and they keep on rotating and moving around in R3. Other example is this again sequence. You can think about time sequence of now positive definite matrices of order 3. So here to visualize it, we're using the one-to-one correspondence between a positive definite matrix and a centered ellipsoid. So you will take the axis to be the eigenvectors and the length to be the corresponding eigenvalues. And we see how those ellipsoids are changing over time. And again, can imagine how the continuous curve may look like. So we're talking about approximation of such objects. And here I'm stating some informal fundamental questions or goals, which this talk will basically will surround them. So we're talking about the function f, which is from Rd to m. Again, in case of curves, of course, d equal 1. And we're given a discrete set of samples. So these samples can be on some segment. It can obviously be a finite segment, not the real line, the only real line. And there is some origin that is of interest of us, where the samples were taken from, in this case, omega. And the first task is to find approximate. So we want to find a continuous object that will approximate the underlying object that we sampled. So of course, there are many details missing here. What does it mean to approximate, in which sense, and so on. But again, it's basically an intuitive discussion at the moment. And the second one is to find a representation, meaning a alternative sequence of elements, and I'm keeping it very general now, that basically reflect some of the essential attributes of F, as seen through the samples. Okay, and we will. This is basically the main part of the talk. We talk about a multiscale representation or a permit transform, which basically provide us with these BJs. So once we understand the problems, we want to say briefly what are the mathematical challenges. Of course, just the tip of the ice. So if we imagine that we record, I don't know, some road trip on the surface of Earth, and we want to approximate it by samples, we don't want to have a result that will imply that we've been like 1 kilometer underground or like floating in air. So closeness is extremely important, and it also gives me the opportunity to emphasize the fact that we know what M is. So this is not kind of line of work that we want to approximate the manifold, to do learning on the manifold. No, we know exactly what the manifold is. There is, we know exactly where the sample we're taking, and we want to exploit this fact. Okay, so we want to use this information to do something more natural mathematically. Okay, some other things that we encounter very quickly is, for example, is the lack of commutativity, which happens in most cases. So things like, even, I don't know, you want to use the Newton formula, you just can't do it very straightforward. You have to say something about the commutator or the operation that you're doing, and so on. And also some fundamental definitions like polynomials and averages and some other stuff that we tend to use almost without thinking too much. In the classical sense, we have to rethink about what does it mean exactly in our setting. Since it's a data analysis seminar, I would say some questions regarding representation. So we want the representation to be to satisfy some compactness. This is like a very broad statement, but we want to aim for some tool that will help us in application like data compression, perhaps defining what is smoothness for such a discrete set of samples. We want to be able to see some local phenomenon. We'll see later a demonstration of this application, and also to cope with data corruption. So denosing, contrast enhancement, and again, stay tuned. We'll get to that. So I will start with a quick recap of approximation, and I will do it using a simple example of the cubic B-spline operator. So this is a functional settings, everything quite classic. What we have here are data points. This is the the dots, basically sampled from function, perhaps measurements that we took, and what you see, the graph, basically the bold line, is the corresponding B-spline. Okay, and it starts. You can also see the dashed line, which is what we call the control polygon. It's just a piecewise linear interpolant, and you will soon see why I also mention it here. Okay, so this is not a function. This is already what the approximation provides us. Given discrete points, we are having a continuous function. So this is easy. We know it, and we know the standard way to represent such a function using a basis. We really like basis. In this case, it's the B-spline's basis. It's a cubic polynomial on the equidistance intervals. It's technical details, but the point is that this is something that it's really standard. So it's good, but if we want to generalize such an approach, it basically forces us to again think about what is a basis, what are polynomials, and so on. But it's also much deeper than that. We're not afraid of the challenge of defining new objects. We want to use the fact that we know the manifold, and more specifically, we want to use locality. And so while B-splines decays pretty fast, in general, it's harder to come up with local basis, and we want to use some other approach that you will see is very natural for these settings. So the approach is called refinement. Okay, so now we're going to define approximation, but instead of using basis, using refinement. So what is refinement? We're taking P0, the most left set that you see there, as our samples, and then we replace it with some other set having more points, and some other set having more points. And we do it mathematically defining a process. And we hope that in the end, the limit of the process could be referred as a continuous function, and we want to have something that we can work, characterize, analyze, and so on. So here are a few examples. So like one-dimensional example in the upper row, you see more and more points, and in the end, it indicates some limit. And then you see this 3D object that basically has points, but also their connectivity. So this is what we call, again, the control polygon, the same control polygon that you saw before in the 1D case. And when we refine it, we also refine the connectivity. And again, in the end, to get 3D object. This sort of processes are termed subdivision schemes. And they were originally came from computer graphics and computer modeling, but we're using them for approximation. Okay, so let's get back to our example. So instead of using the classical approach of just writing down as a linear combination of translation of the B-spline, we're now doing it using refinement. So the refinement rules are very, very simple. So what we are doing is taking all the points and then replace each point with a new point, and in between 2 points, enter a new one. So every time we're doing it, we're adding more points. The limit will be something that dense enough so we can actually refer to the continuous object that we get in the end. And the process itself is very, very simple. When you take a point, you are replacing it with a linear combination of the point and the 2 points next to it. This is the first one, the 1/8 f I1s1 and so on. And in between 2 points, we just replace it with an average, with arithmetic average. This is almost as simple as you can get. And you can see how the locality basically screams from the formula. I don't need anything but the points that near me, the data that stands near me. And in the classical setting, this process exactly generates the same B-spline that we saw before, just in a different manner. All right. So basically, linear subdivision schemes are of the form you can see there. It's just basically linear combination. This is linear subdivision schemes, and there are many of them with many interesting properties. And what we are doing now is called adaptation. So we're going to take this linear combination and exploit the fact that it's actually as a partition of unity here. Again, it's some details that, but we can always assume that. And now I'm going to do a very weird step. I'm going to, instead of looking at this wonderful simple formula, I'm going to look at this one, which is equivalent way to say linear combination. In this case, you can just like imagine you take a derivative, you're left with 2wj f minus fj. This is mainly saying that f, the minimizer is basically this linear combination. So this is very much not too much convenient in these settings. But if we're aiming for manifolds, we don't have the luxury of using linear combination, and we either don't know exactly what it means or it doesn't satisfy closeness. And so we're taking this minimization and define it on the Riemannian setting. So we're taking rho to be the Riemannian metric, and the minimization is done over the manifold. Okay, this is what's called the Riemannian center of mass, because this is the center of mass. Usually the center of mass is referred to, at least classically, when the weights are positive, but it's not a necessary condition. And this is well known. Okay, this is in matrices, this is called the Kircher mean, and for general metric spaces, it's called the Frechet mean. And while it's very easy to define, it's not so easy to calculate. Okay, just to get some sense of what's happened here is when m is linear, it's flat, it's not interesting. But when the sectional curvature is non-positive, this is what it's called Hadamard spaces or cut zero spaces. Then the minimizer is unique, exists for any choice of W and unique. And where you go to positive sectional curvature, things become more and more complicated. So for example, on the sphere where the sectional curvature is constant, we can actually point out which neighborhood allows us or guarantee a minimizer. But also if we have all the condition to guarantee the existence and uniqueness, it still doesn't obey a closed form formula unless n equals to 2. So for any like center of mass of more than 2 elements, you usually need to apply some iterative process if you want to actually calculate in practice. One thing to get over it is to find some kind of finite estimation. You can also iterate, but this is one alternative that we suggest, is using what we call repeated binary averages. And it's interesting because it also gives me the opportunity to talk about manifold average. So we replace each arithmetic weighted average with a manifold average, but what is a manifold average? So this is a nice concept. It's basically a generalization of average as we know it. So just think about the simple arithmetic average here, 1 minus t f1 plus t f2. So this is a function now defined on the manifold. It gets as input these couples of elements on the manifold and spits a new element. And we wanted to satisfy first this property, namely the average of a number with itself is always the same number, right? So the average of an element with itself is the same element. This is the identity on the diagonal. We wanted to preserve symmetry, and we will see it in a second how it's done geometrically. And we want to serve interpolation. So when this t parameter is 0, we are at one end, we're getting p1, and if it's t equals 1, we get the other one. And these are like the most fundamental properties drawn from or motivated by classical means. We have some more, but it requires us to define metric and so on. So I'm just leaving it there, and I want to get more intuitive point of view. So here is a canonical example of such an average.
Presumably it's continuous.
Yes. So yeah, if you define one more property with a metric, you can also imply that it's continuous. Yeah. Sure. There is more to say there. So the correct example is geodesic. Okay, so shortest path between 2 points. It's well defined locally, unless you're in a complete manifold. And in this case, it's just a numerical example on the torus. So basically, we have 2 points, the ends, and the geodesic is basically this shortest path between them. And we can think about the average, here the middle average, as just the middle point. And again, working on the geodesic gives us the entire set of values between t equals 0, t equals 1. And of course, one may also ask what is happened for negative t's or for t is bigger than 1. And it's also a good question, it's actually an important question when it comes to interpolation. It's out of the scope of this talk, so I will just leave it as a teaser. So yeah, all the other properties are kind of very natural from, at least intuitively, from this canonical example. So yeah, let's get back to the example and see what we are doing. So again, this is the very simple refinement tools to generate cubic B-spline locally by means of refinement. What we are doing is basically, I want you to look at this one. So the second one is just an average with t equal half, and this one is basically we write this linear combination as a binary average with a binary average, and then between them another average. Okay, this is what we call repeated binary averaging. And of course, there is no one way to do it. You can play with the numbers. You can write it in very different forms. The fact that the coefficients are summed into 1 guarantee that we can do it. And we actually, in one of our papers, we show how to do it. Like we suggest a way to do it right in some sense, and we argue why you should use it. So for this one, it's pretty straightforward. You just have 3. You want to keep the symmetry. Everything is very nicely done. So here's what we do. We just take our intrinsic average and we replace it, and now we get the same set of rules, but in the manifold settings. So we're giving a discrete set of points, of elements on the manifold, and so we start to refine them. Instead of the in-between points, we're entering the average, and instead of the old point, we're using 1 point before and 1 point after, and the old point to do this 3-stage average, this repeated binary average. And we can get, for example, this curve that I actually calculated yesterday on my computer. So it's a sample of some underlying a curve which we refine to get something continuous, and mathematically, in a sense, now the fun just begins here, because we have to say something about what's going on in here. So can we guarantee that there is a limit, that there is a continuous limit? Can we say something about the smoothness of what's going on here? Can we say something about what is the connection between this curve to the one that were originally sampled? So all these questions are basically ones that we are trying to answer in this field. So this is about approximation. Okay, so now that we know a little bit about approximation, we can move on to talk about multiscaling. And it's interesting because refinement and subdivision schemes are closely related to wavelets. Okay, it's actually a way to calculate mother wavelets, and it's very interesting because the limit of the multiscale basically satisfy the two-term equation that is needed for wavelets and so on. So here we're doing something else, and basically just to keep some picture in your mind, this is what we're aiming to. Okay, this is multiscale. On the right, you have like some high resolution sampling of a curve. This is a curve basically in SE3. Okay, it's some kind of helix translation part, and then some kind of rotation part on as you can see from the green, blue, red axis, how it rotates. And then we have like less details and less details, and we get a coarser approximation. Okay, so to be more precise, we aim to establish the following. Giving this high resolution, sequence of samples, C capital J, we want to do the analysis and decompose it into a lower resolution sequence and the required details. And iteratively doing this process, we end up with this coarse approximation C0 and the required details D1 to D capital J. And also to be able to do the opposite, to do the synthesis, right? Taking this set and basically forming C1 from C0 and D1, forming C2 from C1 and D2, and so on to recover C capital J. Yeah, so questions?
What you just described, if you're given samples, you're given a finite set of samples, right? The same basic.
Mm-hmm.
So like in the previous picture,
Mm-hmm.
I should think that you have the dense sample on the right.
Yes. Yes, this is like Cj, and this is G minus 1 and C minus.
Okay.
Yeah.
You're given all of those stuff.
Yeah. Yes, exactly. It's just a representation. We're looking for a representation. So there is some approximation going on in between, but basically
the goal of the representation is that you can discard some of the details, right, and get a good approximation.
Right. So there are several. I will divide it into two. One is exactly what you said. Like if you're doing this process enough, and if your approximation operator is good enough, at some point the details will be slim and you can throw it away from the window. So this is one thing. The other thing is that you can closely inspect the details and reveal some information about the underlying signal. So this is basically the two.
The information, how smooth it is.
Yes, exactly. Smoothness and some other stuff that we will see. Yes, exactly. All right, this is called a permit transform, and it goes back to 90s. I think David Dono did it first with interpolation, and I will guide you through that, and I will point out what is new and exciting in this part. So starting with interpolation, so you want to have this operator that takes sequence and know how to refine it. It can be, I don't know, cubic interpolation, it could be something else. And the interpolation comes in the form that you keep the old sequence. Like before I told you that we're like taking the data points and replace them with new ones and put something inside in between. So we now keep the old one, we just put a new point in between and gradually refine. So this is interpolation operator. And the interpolation operator, it has this very trivial property. If you interpolate and then you subsample, you downsample, you just get with whatever you started from, right? This is pretty trivial. So this is basically the fundamental property that we use to define the following decomposition. This is the error with 2 is just downsampling by a factor of 2. So C0 is just the downsampling of C1. C1 is higher resolution, and the details is the difference between C1 and how our approximation, or in this case, interpolatory approximation. Our interpolation is acts upon C0. Okay, if you have good interpolation, and if like you have very dense sampling in C1, the D1 will be quite small. Okay, but more importantly is that no matter what, D1 on the say even indices is 0, is completely 0 because of interpolation. Okay, so it means that if I'm instead of C1, I don't know if you have like 10 points, you have after downsampling you have 5 points, and the details hold the information on the other 5. It's unless 5 because it's basically 0 on the others. So you can just replace C1 with D1 and C0 without like needing more place in your memory in essence. Okay, I'm not talking about like how the details decay it and stuff like that. Just conceptually you did nothing. Okay, so now what we are doing now is the non-interpolatory case, and the non-interpolatory case was left undone for many years because the interpolation was good enough, and it was a bit more complicated because now the details also in the even places are not 0 by definition. So what you have to do in this case, you have to define what we call the decimation operator, basically replacing the trivial downsampling with some other operation that knows how to imitate the same formula. That basically saying that in the even places you can discard everything. You could throw away whatever you don't have to keep any information there. So this was known for years, of course, but really calculating it was done recently for subdivision schemes, and it's basically suggests that if everything is linear, if like your interpolation is defined by these alpha coefficients and the decimation and linear are defined by these gamma coefficients, basically they have to obey this convolution equation, and with some knowledge on basically Toplitz matrices and some other known theory, you can derive all sorts of information about the decimation. For example, that it satisfies also partition of unity, something about its decay rate, and it's also if alpha is finite support, it's infinite support, and so on. There's a lot of details here. I can say more at the end, but but basically it gives us, this equation gives us the option of actually calculate this decimation and basically adapt or maybe adjust all this framework to non-interpolatory operation, and we're getting this formulation of the pyramid transform. So given a high resolution sequence, C capital J, we're defining the next level by applying the decimation operator instead of just regular downsampling, and the details as this difference, and we do it iteratively from L equals to capital J till 1, and then the inverse transform or the synthesis is done by just adding the details to the approximation done by applying S alpha to the sequence C L minus 1. So yeah, now we're going back to the manifold valued realm, and here we call this Riemannian set of mass. We're going to keep everything simple for now, and we are doing all the adaptation that I was telling you about, not with this finite sequences and stuff, not with repeated binary averaging. We can, but not now. We're going to do it with the Riemannian center of mass. So giving some non-interpolatory operator, S alpha defined by this linear combination, we replace it with this, like we rewrite it as a solution of minimization problem, and then replace it or refer to as Riemannian counterpart by defining this new tau operator, new tau refinement, basically using the same coefficients as weights, using the Riemannian metric, and solving this minimization or finding the Kircher mean or the Flechet mean each time for each value. So basically, this is the framework. So we'll start with some operator. It can be, I don't know, B-spline. It can be some least squares based operator or some other operator. Depends on the application, depends on how local you want it to be, and so on and so forth. And we first calculate the decimation. There is this equation that we saw before. There's a convolution. We know how to solve it. And then we adapt both of them using the Riemannian center of mass to get the tau that you just saw. And we're doing the same for the decimation to get this Y operator. And now these are the couples. They're like, this is our upsampling operator, and this is our downsampling operator done for manifold values. Okay, so it's actually nicely done by looking at this O plus O minus notation. So I just use it for the exponential and logarithmic maps, and if we rewrite it, you can clearly see the analog to the linear case. Basically, the transform is obtained by taking the higher resolution sequence and applying our new downsampler, the decimation, the adapted decimation operator, and then the details, and this is different from the linear case, is the difference in manifold sense of CL and this operator. But here it means that the DL is basically it lives on the tangent space. Okay, so we have details on the different tangent spaces, and we have all the information that we need basically because it is we know CL minus 1 when we do the synthesis. So we take whatever details that we have, and we refine, and then we add according to the missing details. So before moving to to applications and some numerical examples, I will give you a brief taste of how what is the analysis looks like, not in terms of how proofs look like, but what are like the flavor of results that we are doing. So for that, I'm using this delta. This is the maximal or the superum between two consecutive points in a sequence C on the manifold using the Riemannian metric. Mu is the difference between two sequences with like this joint parameterization. And I also add this straightforward definition of stability, namely that tau, our upsampling operator, is stable if applying it to two sequences, meaning that we're not getting too far away from the difference of or distances of the sequences. Of course, again, there's many details that are missing here. We should talk about locality, its manifold, and so on and so forth. But I want to keep it clean as far as I can. So the first result is about coefficients decay. So basically, this result telling you how the details, the magnitude of the details decay with L. And in this case, we're talking about sequence, and basically it means that it decays proportionally to the distances inside the sequence, okay, with some constant depending on the curvature. So if you think about it, this is true for sequences and for the pyramid that we just defined. But if you think about the sequence as being sampled from differentiable curve and some more details like this arc length, equidistance, the grid, and so on, then you can actually put some more, I don't know, familiar perhaps terms here, so that the details are basically bounded by the superum of the gradient of this curve, and has to do with this P and how it decays. It's 2P minus L. You have more term here, but this is it guarantees the decaying. So this is one result, and the second result that I'm going to show here has to do with stability analysis. So for this one, we use what's called the Rao comparison theorem. So it's basically the Rao comparison theory basically says that if you want to compare all sorts of distances on a manifold, and you know something about the curvature of the manifold, you can compare it to some canonical example of other manifold. For example, if imagine like 3 points on the sphere and you connect them with geodesic, you have this geodesic triangle, and you can imagine that the angles there are like larger than 180, as we know in Euclidean space. And it's also true for the distances. So we kind of inflate our surface, so the distance of the triangle edges is larger. So basically this comparison theorem says that if you have this positive curvature, you can compare it to what happens, for example, in linear, because the curvature of linear is 0 and it's bounded from below the curvature, and then the distances are bounded by what's going on in the linear case. You can do it also the other way around if you want to, if like you have if you know that the curvature is just bounded below not by 0 but something minus something negative, then you can construct this hyperbolic, this canonical hyperbolic manifold, and to bound your distances which will happen on this specific manifold where you can actually, when you can actually calculate explicitly what's going on there. So all this intro is just to show what we have. So it is a very specific case, but it's good enough for us at the moment. So what we see here are like we want to bound the distance between two high resolution sequences where we started from something that is somehow close, and details that in this case we have this assumption is not necessary, just nicer when we have some with some details. And basically it says that the distance is bounded by the initial distance plus the difference between the details, and here the difference should be calculated very delicately because we're talking about basically vectors that lives in different subspace, different tangent spaces. So we have to parallel them to common place and then to look at the difference. So this is how it looks like, and I think now we're ready to look at some applications and some numerical examples. So yeah, we'll start with the sphere just to get some intuition for the multiscale here, and this is this flower or star-like curve. We have it. We have like a closed form. It's smooth and everything, but now we sample it and then we apply the analysis according to our pyramid. So one thing to look at is the y-axis, the magnitude of the details. What you see here are the details, and you can see how it drops: 0.18, 0.01, and a 0.007, and this is already 10 to the minus 5, and this is totally aligned with the decay result that we saw before. So it also indicates that the curve is smooth. Okay, so it's a way for us to quantify what is a smooth manifold, curve on the manifold according to its samples. So what we did here is to add some noise to it. It's not that beautiful anymore. And when we take these samples, we definitely see that the previous property does not hold anymore. So you can see here there's some decay, but then it stays here and stays the same magnitude, and it doesn't obey really this nice geometric decay that we saw before. And this indicating also the other case, that something here is not totally aligned with our way of measuring smoothness, for example.
Is there any, how are the coefficients ordered? Is there any meaning to the x-axis?
Yeah, so yeah, we basically sampled it, and just to avoid the discussion on boundaries, we did it like periodically. Okay. And so the coefficients are just according to the samples. Okay. Yeah. And I think it will be clear in a second for the next example, or the next one after it. So what we did here is basically denoising 101. So you have representation, you have noise. So we just eliminate some of the coefficient below some threshold, and this is what we are getting. So basically some smooth estimation for the first curve.
So you're doing a hard threshold?
Yeah, just hard threshold.
Is there a harder way to do that? Shrinkage type of
probably yes, but not yet. Yeah, we can do it after the talk. Yeah. So yeah, there is a smart way to do it, but we didn't search for it yet. So here's another similar application. It's called contrast enhancement with images. It basically means that we see more natural version of the image. In our case, sorry, what we did is basically scaled up the details coefficient of our multiscale, and this is over a time sequence of SO3. So we apply it on this axis, and we just visualize it on this along a line. And this is what happens. So originally we took this one, and we applied the Fermi transform. We then scaled up the details, and what you see is that any twist becomes much more dramatic. And for example, here you can see, I think as far as you can tell from there, and take a look at here and what's going on, and it occurs across the board for the entire sequence, and sometimes it's useful. So here is another application. It's called anomaly detection, and in this case we're taking a sequence of symmetric positive different matrices. We already saw it in the beginning. So this is a sequence, and what we did is basically we took some filter, and at this point we kind of we're shrinking all the eigenvalues. So it's basically gives the same ellipsoids but smaller. Okay, but it's clearly has something going on in here. So you see everything in one scale, progress smoothly, and then something happened. It continues moving smoothly, and then again something happened. Imagine something like this step function, and so we apply the Fermi transform. We're using here the quadratic B-spline or the cubic one, and this is what we get. So on the left side, this is the original one. You can follow the magnitude and see again the nice behavior, the nice decaying here, 0.4, 0.06, 0.007, and so on. And on the other hand, you can see that it stays quite big, but in fact it doesn't stay quite big. It stays quite big only in certain places, and this is the places where the jump discontinuity occur. So you can see it clearly on this one, on the first one, and on the second jump point. So this tells us, it gives us an automatic indication of something that happened there. So this is where locality kicks in. So at this point I'm stopping. I have I want to give you some taste of some other things that we are doing in similar problems. So just outside of what we just saw. So one thing that I already mentioned is that when we define the pyramid and define the subunit schemes, is just the first step, and then we have to analyze it. So we're talking about the analysis tool, but then we're also interested in some other settings. So for example, one interesting setting is the Hermite approximation. So in this case, it's basically a curve in R3. Everything is linear space, and you can see like it's you have like a point and the tangent of the curve in a certain place, and this is a refinement of this curve. This is what it looks like, and we also want to do it in nonlinear settings for manifolds. So this, for example, what's going on the sphere. So you just need to take a few points in the tangents there to really define a smooth curve that fits into the samples. One more thing that we are doing is extrapolation. This is all different ball game. So it's really exciting. And the one thing that I can tell you that is much harder than approximation. And lastly is like higher dimensions of the domain. So we talked about curves, but it's not always the case that you got curves. Sometimes you have surfaces. This is a classical scattered data approximation of a surface. You have some kind of square here where you got values of some function, and you want basically to form the approximation, and we do the same. So this is an example of scattered data approximation over SO3. This is actually, what you see here is basically visualization of the entire function. And this is where places that we sampled, and we're doing some multi-scaling approximation. So it combined a combination of both approaches that you just saw. And we can do all sorts of things like, for example, denoising. So this is some corruption of the function, of the smooth function that does so, and this is the denoised version. Yeah, so I think I will wrap up this talk. I must thank two of my collaborators that specifically for the main topics of this talk, which is Niradin and Wael Matar, which is my PhD student. It's actually, Niradin was my advisor and Wael is my student. So this is like the entire chain here. And there are some other collaborators on the topics that you just quickly recapped in the last slide. That's it.
Okay, so if there are any questions for Nir for the people at home, you can just type them into the Q&A box or into the chat.
I'll ask one question.
Sure.
Excuse me. So there's different ways to represent a manifold. You can do it by coordinate charts, atlas, or embedding, or level set, zero set, et cetera. So do your methods prefer one representation? How do they depend on the representation?
So this is the thing. We work with manifold values, but we really interested in them in the objects that define with manifold, like objects like curves on a manifold, or like in general function that has manifold values in the range, not in the domain. So usually the two important things that we kind of need from the manifold to know from the geometry is the metric and a way to define average. So the question is basically, I think, about the second one. So it depends on the average and how we define it, and some averages prefer some other representation. We actually use a lot geodesics, and geodesics in matrix Lie group, usually geodesic of connecting just two, you actually have like closed forms and stuff like that. So we kind of avoid mostly this question, but it's about how to basically define the average. Analysis is something else. In the analysis, it depends.
Even for averaging, even in the case of the orthogonal group, there's lots of papers on how do you define the average of a bunch of orthogonal matrices.
Right.
There's a lot of work going on just that one.
Definitely. Right. It's I think it's a fascinating question.
For the center of mass that you define, how like in some of the examples, how do you compute it numerically?
So I think that in the examples, what we did is applying this gradient descent method. You basically start with something like some approximation. It's going to be with like repeated binary averages or something else, and you do gradient descent. while if you keep small amount of elements like 3, it's quite fast. You don't have to work hard. If you do more, then it's a question, and it's interesting. I was mentioning extrapolation. So one application of the extrapolation that we are working on these days is to accelerate such optimization. So we showed, for example, that if you're taking 100 positive definite matrices and looking for the center of mass, we can accelerate the Riemannian gradient descent by a factor of, depends, 3 or something, just by using a smart extrapolation. Yeah, but at least here we just use Riemannian gradient descent.
Okay, thank you, Nir, for a very nice talk. If there are no more questions, then we can conclude. So, thank you.